In this lesson, we're going to talk about a modeling application called optimization. So, what is optimization? Optimization is a real-world term for finding the maximum or minimum of something. And max and min are sometimes called extrema, by the way. And extrema is just the plural for extremum. So a maximum is called an extremum, and so is a minimum. For instance, we might find the maximum profit a business can make given their revenue model, or we can minimize the amount of a material needed to construct an aluminum can given its volume. So those are some examples of optimized things, maxes or mins. All right, these are some steps for optimization, and these might seem a little kind of just vague at first, but it'll make more sense once we actually see a problem. So we want to read and understand the problem, of course. Sometimes we can draw a picture if that helps us. We want to then write a model equation for each situation. And we might need to recall some basic geometry formulas like the area of a square, that kind of stuff. There are geometry formulas that are given to you on your formula booklet that you'll have for your exam, but I won't make you memorize any of the hard ones. I'll either give it to you or it'll be in the formula booklet, so don't worry about formulas. We'll then use substitution to write one of those equations in terms of one variable only. And this step is not necessary if your function, of course, is already in one variable. So then we want to find the max or min of the function you're trying to optimize. That can be done easily with our graphing calculator. Just do second calc, and there's a max button and there's a min button. And then you, of course, want to verify that you've actually answered your question being asked with units, if applicable, if there are units. Sometimes there are, sometimes there aren't. All right, let's get into it. So we are going to find the area of the largest rectangle with a perimeter of 200 feet. Okay, so what we want to do here is, for this example here, if you're familiar with the perfect rectangle, which is a square, you can actually already figure out this answer without doing any optimization. Because if you have 200 feet and you're a square, that has to be 50 feet, right? Because 50 plus 50 plus 50 plus 50 is 200. But I want to use this problem and to go through the full steps, because obviously this is an easy one, but it gets harder. So what we want to do is we want to ask ourselves, what are some formulas that we can actually write down that are functions? And perimeter is, let's just draw a rectangle here. We've got two x's and two y's because your lengths are the same, your widths are the same, and the perimeter is just adding those together. So we have two x's plus two y's equals 200. Now, this 200 feet that is the perimeter. This is a constraint for perimeter because perimeter is not changing. We don't know what the area is. That could be anything, but we definitely are constrained by exactly 200 feet because we know that for sure. So we call the constraint equation the equation that has a number. Then we have what's called the optimal equation. We want the area of the largest rectangle. So we want to find a max for area. Okay, so our optimal equation is area. What is that? Well, area of a rectangle, that's x times y. Okay, now let's remember what our goal is here. To find an optimal, or to find a maximum, we literally could just type this in and type the max button. That would be the entire problem in our calculator. However, we have two variables, a function of two variables, and we can't have one equation that has two variables and solve that because we won't get an answer because we have too many variables. So instead, we need this to only have one variable, and then after that, we can get the max in our calculator. So what do? We go to our constraint equation, and we solve so that we can have a substitution. So let's do minus 2x. You could solve this for x or y. It doesn't matter, but I'm just going to solve for y. So we'll get 2y equals 200 minus 2x. And then we're going to divide everything by 2. Divide both sides by 2 to get 100 minus minus just x. All right. So this right here, we're going to substitute. We're going to substitute this in. So that's going to get us area equals x. And instead of a y, I know what y is in terms of x. Being in terms of something means that there are only that one variable. This is called in terms of x because there's only x's now. And now area is in terms of x as well because there's only x's on the other side of area. Okay, so now we can use our graphing calculator to find the max of this. So let's go to our calculator. You are allowed to start putting stuff in your calculator and find the max once you have one variable. And you'll notice I'm putting the unsimplified version of this into my y1. So I'm just in my graph screen, y1 here. I didn't distribute it. That's actually very important. I mean, I could distribute, but your calculator doesn't care if it's simplified or not. Don't waste time and energy and potentially make a mistake for doing a step that is not necessary. All right, so we're gonna go ahead and I'm gonna do zoom standard just because, like, you know, it's good to see your normal zoom. And oh, okay, turns out this graph is like really, really big, like it's going way off the screen. So we know that we can auto zoom, that's zoom 0, that's called zoom fit, and then it'll auto fit your graph. So let's see what that looks like. Okay, so it zoomed out some, but the problem is that we want to find a maximum. We want to find the top of a hill or something. Otherwise, we're not finding an extremum. So it looks like we have to zoom out even more, which is fine. Let's zoom out this time. We'll see if that looks good. Yeah, so I'm just kind of playing around with it. You want to just try to zoom until you figure out the hill. Oh, I think we're almost there. Let me try to zoom out one more time. Zoom 3. One more time. Aha, there we go. You clearly see a maximum. All right, so let's do second calc, and then we're going to go to maximum. That's 4. Okay, and it asks you left bound. I'm going to hit enter, and then it hits right bound, and we want to capture that maximum between your left and your right bound. So I go hiya, 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 hiya. Yeah, I always say that when I'm scrolling. It's like I'm attacking the right arrow button. Hiya, hiya. Okay, so let me do enter for right bound, and then it says guess, and then it'll kind of like bounce between those and kind of zoom in on your answer. So you hit enter again. All right, there we go. Our maximum is 50 feet, which we knew was going to be the answer already for x, but this is how you do it for real. Okay, you also notice there's a little bit of rounding error that your calculator does. This is, you know, don't do all those decimals. This is 50, okay? It also gives you a y of 25, and this actually is a model for area, and that's what we're looking for. We're finding the maximum area. So this is actually our final answer, but let's go see how we would do that the by hand way, because your calculator doesn't give you all the answers. Okay, so when we solve, we put an implies that sign. So this algebra equation implies that x is 50. Okay, for our max. All right, so this is 50 feet. All right, then this is not the answer though. We didn't actually answer the question. Find the area. Okay, so how do we find area? We need a length times width. So I have a length times width right here, x times y. So let's find our y. Our y is, well, right here we got a road map. We got 100 minus x there. 100 minus 50 is 50 feet. That's our y. So our area is when we put all that together. Our area is 50 times 50, which is 2500. Here we go, units, feet squared. Feet squared for any areas. Why is it feet squared? Because we have x times y, which is feet times feet, and anything times itself is squared. That's why we call it feet squared, folks. All right, boom, we got 2,500 feet. Very nice, our first optimization problem. Let's look at another one. All right, so for this second one here, it says if a box with a square base and an open top is to have a volume of 4 cubic feet, find the dimensions that require the least material. And we're going to neglect the thickness of the material just to make the problem a little bit easier. Okay, so this is like, this is a lot. So you know what, let's actually start just by kind of drawing a picture here. I'm going to draw a square base. Square base, and then we want this, it's like, I guess it's going to look like a sort of a bread box. So the way I draw prisms is I kind of just draw 2 congruent shapes, then I just join all their corners, all their vertices, and there we go. There's our bread box. Okay, so it also says we have an open top, okay? So what that means is that maybe we'll consider this to be the top. I'll just kind of shade it in because it's open. We have an open top bread box. So what that means is we only have the bottom of the box, but not the top, of course. Okay, so let's go ahead and start to label this. Because we have a square base, we actually have, I can label this S, and s because they're the same. So squares, usually we say side squared. Okay, so we got s and we have the height. Okay, so let's look at what some equations would be. We have our constraint equation here. This is our constraint equation because we have a number for volume. So let's just kind of write out volume then. Volume is length times width times height, but let's actually use what we have in the problem because 3 variables is a lot. So we're going to rewrite that as s times s, which is s squared h. And that is equal to, it says 4. All right, very good. Okay, then we want to then construct our optimal equation, the least material. Whatever it says the most or the least or the maximum or the minimum, that is your optimal equation. This is our optimal. So we want a min for surface area. Okay. Surface area is not a formula, folks. I mean, there is a formula for it, but the whole point of this lesson is about modeling. We want to construct an equation, a function that is the same idea as this picture. We want to re-represent a box with an open top, but with functions. Okay, so how do we do that? So let's start writing surface area. Well, let's think about what shapes we have. We have one square. Well, one square's area is s squared. So let's just write s squared. And then what else do we have? We have these 4 rectangles that are all around our box, that are the sides of our box. So 4 rectangles. So 4 length times width, which is s times h. So this is a square plus 4 rectangles. Okay? So this equation models this picture for surface area. That's a big understanding of this lesson. That functions model real world situations. Very important. Okay. Now, the problem is that this function has 2 variables, and we need only 1 variable. If we only had 1 variable, we wouldn't need this constraint equation. We could just throw it in a calculator and hit the max button. But we need to solve this for a variable. It looks like h is probably going to be our easiest bet here, just because there's only 1 h there. So I'm going to divide the s squared over, and I'm going to get h equals 4 divided by s squared. All right, so let's go ahead and put this into our surface area equation. So we got surface area equals, we got s squared plus 4s, and then h is 4 divided by s squared. Okay, all right, fantastic. Now we only have 1 variable. Now you could do 4 times 4 is 16, you could do s, and then one of those s's cancel, but we're going to keep in the spirit of don't simplify because our calculator can do it for us. So s squared plus 4s, and then 4 over s squared. So we got, let me delete this here. Delete. All right, we got s squared. We have just the square, so x squared. And then we added on 4 those rectangles, which was 4 times s, which we call x, times 4 divided by x squared. Okay, so let's zoom standard just to see what it looks like. And all right, it looks like we're not seeing enough, so let's zoom out again. Zoom 3, hit enter. Aha! Okay, we see a minimum here. That is where we want to zone in on. However, a minima means the lowest of something, and you'll notice that the graph goes even lower down here. However, all of this over here is called extraneous. Extraneous is parts of a function that it looks like it's there, but like think about it in the real world. What does it mean if x is negative? That would mean that our side length of a box is negative, and we can't physically have negative 4 feet, right? So all of this blue, all of the left side here is, don't look at that, because that's not really there. Okay, so we're going to second calc, minimum, and it says left bound. Let's pop over higher. Okay, all right, we're already there. All right, so we're going to enter, and we're going to right bound. We're going to bound our min on the right, higher, and then guess. Yes, we're going to guess. Okay, so this is x equals, it looks like we have 2 there. Okay, so we have x equals 2. So s is 2, and what was that? Cubic feet? Or no, yeah, so we're in feet. So that's going to be feet. Now, we then want to make sure we answer the question. What are the dimensions? That's all we want are the dimensions. Well, we found one of the dimensions. And what are dimensions? Well, we have like a length times width times height. And we already found the length and the width. So now we just need to find the height. So let's do h. Let's find h. H is, oh, we have 4 divided by 2 squared. So let me do this. 4 divided by 2 squared. That is 1. Okay, well, would you look at that? 1 foot. All right, so let's put it all together. What are the dimensions? The dimensions are 2 feet by 2 feet by 1 foot. These are our dimensions. Dimensions are what are all of the measurements that make up your box. So 2 foot by 2 foot by 1 foot box. That gave us the least amount of material. Would you look at that? All right, very cool. So what I want to do next is, for example 3, for the next example, it's very similar to example 2. So I want to use this. Oh, I was working out the problem a different way. Don't mind that. Oh, yeah, actually before we get to that, these are the geometry formulas you get in your formula booklet, just for your reference, so you don't need to memorize those. But like I said, for assessments in this class, I'll give you any of the more difficult formulas. Okay, for this next example, I want to use this as a you try. I want you to try this, okay? So you're going to go ahead, I'm going to explain this a little bit, and then you're going to pause the video and try this, and then I'll just display the solution, and then you can read it before we move on to the final example. Okay, so you're asked to design a 1 liter, which is also known as 1,000 cubic centimeters, oil can that's shaped like a right circular cylinder. And what are the dimensions that will use the least material? So I gave you the volume and surface area formulas for a cylinder. Now you're going to use the least amount of material. So I gave you this little conversion here because you need units that are not liquid only units. So you want to use units that actually measure length as well. So use 100 when you do your volume formula. So you're going to set volume equal to 1,000. That's going to be your constraint. I'll actually get you started off on this. Pi r squared h equals 1,000. That's your constraint. All right. And then figure out what dimensions make the least material. See if you can do this. Go ahead and pause the video, give it a try, and then we'll come back. Okay, so we're back. And here you can see your solutions. If you need to pause the video, then you can pause to check. All right, so let's look at one final example. This one actually is not as much of a real world problem as it is involving a given function. So we're going to determine the maximum area of a rectangle with vertices on the x-axis, and our function is this parabola here, which I gave you here, okay? So what does this actually look like? Well, we have the vertices on the x-axis. So that would be like your rectangle is kind of like sitting on your axis, and it has vertices on the parabola too. So it's going to kind of like reach up towards the parabola. Now, I'm just drawing like, you know, I ended up drawing a square. It's not necessarily going to be a square, but this just gives you an idea of what it's actually talking about. We want to maximize the area of that rectangle. Let's just kind of label this, okay? Because we have a function here. And a function, what it means to be a function by definition is a height. So this is a y value. This is a y value, or a height. What does that mean to be a height? It's the distance from the x-axis all the way up to the parabola. That's what it means to be a function height. So I'm going to label that y, okay, which equals -1/2 x squared plus 8. Okay, so let's think about what x actually means. X is the distance between 0 and wherever we're going to. So that's x. Well, symmetry, the other side, is also x. Okay, all right, so there's just a little bit of labeling here. All right, so then what we want to do, let's just think about what our constraint is. Our constraint is any distance that we definitely can like see or visualize. So this is our constraint here. So then we have, what do we optimize? The area of a rectangle. So our optimal is going to be area, which is length times width. But that has two variables. We want one variable. Well, let's think about what we actually have here. We have a length. We have a width. And we need one variable. Well, look, we got x's and we got x's. So let's do a little substitution. This is very, very little clever here. Okay, so our length right here is right here. Negative 1/2 x squared plus 8. What's the width? We got two x's. Aha! One variable, only x's. This is good. All right, so that actually was a little bit tricky to create this model, but this is a model for our area, a length times a width. All right, so let's go ahead and get that knocked out. We had negative 1/2. We have negative, I'll put this in parentheses, negative, I'll just say 0.5 x squared plus 8, and then times 2x. Okay, and then we'll go ahead and zoom 6 just to see it in a standard mode. Oh, and we want to maximize the area of the rectangle, so it looks like it's going to maybe top out right here. So let me just do a quick zoom out, zoom 3, boom. All right, much better. All right, we see the max there. That's where we want to go. Okay, let's do second calc max. Second calc max. So left bound, let me go hiya. All right, go boom. And then I go hiya, 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 hiya. Okay, we got right bound. Guess? Yes. All right, boom. We got 2.3094. I'll just grab a bunch of decimals. So our x is, so this implies that x is 2.3094. Now I'm going a few decimals out, okay? Don't just do one decimal, because we're going to use this to make an additional calculation. So you want to grab more decimals in what's called an intermediary step. So there's no fast rule on how many decimals to go out for intermediary steps, but just grab enough so that your final answer is more accurate. Okay, so if our x is this, then we can calculate a y. Okay, so our y, what is our y? Well, boom, we got a roadmap for y. Negative 1/2, 2.3094 squared plus 8. Let's grab that real quick. Negative 1/2, negative 0.5, parentheses, we had 2.3094 squared plus 8. 2.3094 squared plus 8. All right, that's what, 16 thirds, 5.333 repeated. All right, very cool. So equals 16 thirds. All right, so let's put all that together. Area equals 2.3094 times 16 thirds. We want to make sure we're actually answering the question. It says what's the area, so we're doing length times width here. And that's going to be, let's multiply that by 2.3094 times 2.3094, enter. 12.3168. So let's write it down. 12.3168. Now, we don't have a standard convention for how far out to round for now. Don't worry about that. We haven't talked about significant figures, so I'll just grab a few decimals to make it as accurate as possible. You'll notice that there are no units. You don't put units squared for theoretical problems, okay? If there's no units, you just don't put any units, and that's okay. All right, very good. So a bunch of examples on optimization. Thanks for sticking with me here. Hope you found this helpful, and let me know if you have any questions.